Hello and a very warm welcome on behalf of NTi Audio. Today we are talking about the basics of FFT analysis. This webinar is actually a first part of two. The second one will be presented soon with some more in-depth information about FFT analysis. Today we are covering more the basic concept of this measuring method and the related implications. My name is Markus Becker and I'm assisted today by Greg Schmiedle. He is the expert who is answering to your questions. The contents that we have prepared for you start with an introduction why and what for FFT is a good measurement solution. We will then follow with an in-depth side of the FFT calculation procedure and the related implications that need to be considered. We have also prepared a practical presentation for you where we will show you the details and aspects that we have introduced before. Finally, we will wrap up the contents and provide some additional hints before we come back to your questions and possibly provide some more comments on your questions. FFT is a very powerful, a very helpful tool for analyzing the details of an audio signal, for instance. Let's say you have an audio signal, a distorted signal where you measure a certain THD that is out of range. You may like to know what is the root cause of this distortion. So a look at the FFT, at the spectrum of the signal, will allow you to identify odd harmonics, even harmonics, non-harmonic distortions, all that stuff that may be the reason for the problem. So it is a very helpful tool for troubleshooting, but also for fine-tuning if it comes to optimizing the performance of a certain device. Another typical application is production testing, where we want to find out whether a manufactured item is working correctly or not. Well, if you have ever used an FFT, you may know a couple of these parameters that are typically adjustable. The size of the block length, windowing, averaging, scaling, all these parameters and some others are very important to adapt the FFT to your specific application, to your demands. So it is of course essential to understand what these parameters stand for and how to use them properly. And that is what we want to show you in this webinar. But let us first clarify the fundamental operation of an FFT. What is it actually? It is a method to calculate the spectrum of a periodic time signal. I will say something more about this adjective periodic, but let me now take a look at the basic principle, what is happening in an FFT. Let us assume this is a time signal. Now, we can decompose this time signal, if it is periodic, in its sine components, which means every periodic signal is a combination of single sinusoidal oscillations. And the FFT basically decomposes the signal, which means it shows you the levels of the underlying sine waves in the frequency spectrum. You can see that here these blue lines indicate the levels of the corresponding sine frequencies. So we are translating the time signal into the spectrum. By the way, you could also do the other way around. You could start with decomposed sine waves, combine them, and then you will get back this time signal. How does it happen actually? The first step is you take the time signal and you cut out a certain piece of it. So this is the capture window. And this part of the time signal in this window will be sampled, it will be digitized, and here comes the first key parameter into play, the block length or the size of the FFT. And this term block length stands for the number of samples in this capture window. And this is important that this number has to be an integer to the power of 2. So I have plotted here a couple of typical block lengths. You can go below, you can go above. This is just an example. Now, the next step is symbolized by this formula, which I will not explain in detail. But what happens now in the core procedure of the FFT calculation is that you decompose the signal. And this happens like that. You determine the correlation between a sine wave with the time signal. What is very important that this sine wave has to fit exactly into our window, and then we calculate how closely correlates the sine wave with the time signal. And the corresponding result will be plotted here in the spectrum. So this gives us kind of this level here gives us kind of the correlation between this specific sine wave and the time signal. Now we repeat the process with again a sine wave with the higher frequency, double the frequency of the first one. Again, this sine wave fits exactly into our capture window. And we get again a correlation which we plot here in the spectrum. So we proceed step by step, frequency by frequency with this procedure. I have plotted here a sine wave which apparently is pretty much correlating to the time signal, and that is the reason why the corresponding level here is much higher than the previous levels. We continue. This is another example of a pretty good correlating sine wave, and in the end we have the spectrum in our bandwidth of interest of this decomposed periodic time signal. That is the core of the FFT calculation procedure. What is important to keep in mind, the name of these levels is bins. So each of these points here, each of these correlation values is called a bin. And the second thing that needs to be considered is that the distance between two bins on the frequency axis, on the linear frequency axis, this delta F is always constant. That is the frequency resolution of the FFT. And I will say a little bit more about that. But it is important to know, to understand that this delta F is constant for the FFT that we have just executed, and we cannot go below this frequency resolution unless we change the block length. And that is what I show you on this slide. Because the sampling rate and the block length have important implications. One of them is that the size of the block length, the number of samples, apparently have a direct correlation to the duration of the FFT acquisition. The duration per block is given by the number of samples. Second, the block length has also a direct impact on the frequency resolution, the delta F that I just showed you before. And I want to illustrate that in a practical example. Here we have a sampling rate of 48 kilohertz. That's the sampling rate of our test instrument. And we have a block length of 512 samples. Now we can easily calculate the duration of our FFT acquisition, which is 512, the number of samples, divided by the 48 kilohertz. And that gives us 10.67 milliseconds. The next step, we can calculate the frequency resolution. We invert this 10.67 milliseconds, and that gives us the frequency resolution. The 93.75 Hertz are the frequency resolution of the FFT with these two given parameters. It becomes obvious that if I increase the block length, if I double it for instance, I reduce the duration of the block. Excuse me, I increase the duration per block, but I reduce or minimize the frequency resolution. There's another, a little bit more complex implication of this FFT acquisition, and that is called leakage. And it has to do with the fact that our periodic time signal, or its components, typically do not fit exactly in a FFT block. Let me explain that here on the sketch. Let's assume we have a perfect sine signal. We would assume that the FFT spectrum of that sine signal gives us a clear bin here at the corresponding frequency. However, this is not always the case. And why? Let's continue with this ideal case. Our cutout capture window hosts exactly this sine wave, and it just fits exactly into that window, which means the terminating level is the same as the initiating level. The FFT calculation procedure always appends the captured signal, the sampled signal, and assumes that it is continued into eternity or forever. That is the mathematical procedure that is underlaying this process. Now, if I have this case where my sine wave or a multiple of my fundamental period fits exactly into my capture window, I have here a smooth transition and the sine wave looks nice, and that would actually give me such a picture. However, in most cases, in reality, the situation is normally different, because this sine wave from my time signal or its components do not fit exactly into my capture window. So the terminating level is different than the initiating one. And what happens now in the FFT calculation procedure, this part will be cut off. We append this part of the signal here, and this gives us here a clear discontinuity, which is repeated, of course, every time a step here at these points. And this discontinuity has the implication that it causes leakage or smearing effect. So you see here the peak level is still the fundamental frequency of my sine wave, but instead of a singular bin, I have some more results here on the left and on the right hand side, low and high frequency components that are caused by these discontinuities here. Well, this is of course an effect that we are not very happy about, because it somehow falsifies our result. It does not show the reality that we see here in our originating signal. And for that reason, we have to find a countermeasure. And a good working countermeasure is windowing. So this is a measure to reduce the leakage by smoothing the transitions, because that is the major goal. We have to smoothen the transition from the starting point and the end point where the two signals come together. And let me show how this is operated. Here I have a typical windowing function. This is a time function, and it is a kind of an attenuation of my signal. So that means that the starting part of my time signal is attenuated in a way that it starts across the zero crossing line and it ends again at the zero crossing line. So after applying my attenuation, the signal would approximately look like that. And now if I append this signal, what the FFT does, a second time, you see I get a nice smooth transition here, and that reduces the smearing, the leakage tremendously. If I take another example here, the picture from before, a sine wave without windowing would look like that, and as soon as I apply such a windowing, we get this result here. We see clearly the dominant bin, the dominant fundamental frequency of our sine wave, together with some harmonics. Now let me show you that in a practical example. For that purpose, I have here two test instruments on my desk, the FX100 audio analyzer and the XL2 handheld analyzer, both of them controlled by my PC, has installed the FX control software and the XL2 projector software. Both of them come along free of charge with the two instruments. In between, I have an amplifier, and I'm gonna switch over now to the FX100. This instrument offers a big variety of parameters that you can amend and optimize for your application. I'm generating now a sine wave with 750 Hertz. I start the measurement, the generation, signal generation, and the measurement. You see up here the time signal of that sine wave, and down here we see the FFT spectrum. And you can see what we would expect, a nice clear bin showing us the 750 Hertz from our generated signal. If I, however, amend the frequency all of a sudden we have heavy leakage, we have heavy smearing effects. So the reason for that is the 750 Hertz sine signal fits exactly into my capture window. And as soon as I get away from that frequency, I can also increase it. I will immediately have these leakage and smearing effects. Let me show you that in another picture, a more detailed picture. Here we have again the generated sine signal. Here we have the time signal as it is captured and repeated by the FFT calculation, and down here the spectrum. Now I do the same as before. I amend the frequency, and you see immediately here we get these discontinuities, these steps that are causing our smearing down here. And I can have different shapes of this discontinuity. You see it here. Now this depends from the exact position of the sine wave in our capture window, and so on and so forth. But this is the root cause of our smearing. What can we do against? I said it before, we can activate a window, and that's what I'm going to do now. You see it? Here I have now my fundamental frequency and an underlying noise to the left and the right hand side. Now there are two things that you may notice. First of all, this harmonic or this fundamental frequency is pretty wide. Can we do something about that? Yes. And the second point is you may notice that it seems as if the frequency spacing here in the low frequency range is higher than here in the upper range, and I will come back to you just in a minute. But let us start here with this width of this spectrum of this bin. And that has to do with the resolution, with the block length of the FFT. If I increase the block length, I get a higher resolution, and we get closer to this picture that we also saw before, that we would expect a very neat and narrow bin here at the corresponding fundamental frequency. Now let me switch over to the linear scaling. The graph that you see here is logarithmically scaled. If I switch over to the linear scaling, this is actually how the result would like when we look just at the FFT data. The FFT result, or the result of an FFT spectrum calculation, is always plotted on the linear frequency axis. Of course, we can also plot it logarithmically, but normally it is linear. And if I reduce this number of points here, this is the number of points that you see on the graph. If I say I go down to 100 points, then you see now here we have this equidistant delta F. Here we have the frequency resolution throughout the x-axis. But this applies only in the linear scaling. In the logarithmic scaling, if I switch back, here we will have this effect that the low frequencies, apparently the logarithm stretches the lower frequencies, seem to be wider than at the higher frequencies, but on the linear axis actually it's the same. I can even go to the other direction. I could double or increase the number of points, and then you see here that's the effect. I get a finer resolution of my displayed result. Now I would like to show you another test signal to demonstrate the powerfulness of this analysis method. And now I'm going to activate an audio file that I've pre-recorded. Actually, it will be a pulsed signal. You will see that in a second. You see up here the pulses in the time domain, and down here the spectrum. This looks a little bit awkward, and now let us switch back to the linear scaling, and here you see now what's happening. Apparently I have a lots of harmonics that together with the corresponding levels give me this pulse. So this is the decomposition of this signal up here. And I would like to show you even another signal which demonstrates this effect very nicely. This is the composition of a rectangular signal. We start with the sine wave. You see here this frequency. We add an harmonic and a third one and a fourth one and so on. And with every harmonic that we add, we optimize the square wave here in the time domain. The rule that applies on the square wave creation says that you start with the fundamental frequency, we'll see it now again, and then you add 1/3 of the third harmonic, 1/5 of the fifth harmonic, and so on and so forth, and that gives us altogether this nice square wave in the end. So here you see a typical application where you could analyze the fingerprint, the characteristic of a signal that you are analyzing. I want to show you one more parameter that you may amend, and for that purpose I'm going to activate now a pink noise signal. And you see here the corresponding frequency spectrum seems to be a little bit, not nervous, but it's not very steady. That has to do with the characteristic, the nature of pink noise, but we can smoothen that curve by activating the averaging. Averaging means that we are sampling several blocks of FFT and then we are calculating the average of these blocks. So I have activated that, and you see now it comes much smoother and narrow, the corresponding result. So this is another parameter that you may activate in order to get the picture as clear, as relevant as you like for your application. Let me now swap over to the XL2 analyzer, which also offers an FFT with a little bit less possibilities to parameterize it. We see here we have a 20 kilohertz bandwidth starting at 480 hertz up to 20.45 kilohertz. But in this case, for instance, I apparently have some effects here in the low frequency range. And for that purpose, you can zoom into that low frequency range by pressing the Pages button on the XL2. And then you see now we have reduced the displayed bandwidth to 1.7 kilohertz. We see now much clearer what's happening. And here we have a fundamental and some upper harmonics, some apparently. I can even go down further to a display of 200 hertz, starting at 7 hertz up to 215. So this is now my display range, and here I get a clearer picture of what's going on. I can use the cursor. I can switch it to automatic mode. In that case, it will automatically jump to the peak level in my spectrum, or I can switch it to the manual mode, and here now by clicking I could scroll through the spectrum with the corresponding results. I can even, if I like, you see up here the information by pressing the limit button and scrolling, I can even amend the displayed bandwidth. I'm going to show you that very briefly. You see now I have cut down the displayed range from 200 hertz even to 100 hertz. So this is a very nice tool to scroll and pan through this spectrum in order to analyze the exact details of my spectrum. One more hint in this regard, the XL2 always applies a window, the same as the FX. FX, however, you can switch off the window. In the XL2 it is always present, and here we have the selection between two windows, the hand for general purpose acoustic measurements and the Dolph-Chebyshev for small signals close to a dominant signal. Okay, let me get back to my presentation and summarize the key points what I have shown to you. First of all, the basic calculation principle of an FFT. We start with cutting out this capture window from the time signal. We sample it. The FFT will append the sampled signal to it. Of course, we also apply the windowing in order to get smooth transitions, and then we calculate, or the system calculates, the FFT spectrum. Typically, you may first adapt the block length. Keep in mind, a higher block length means a longer duration, so the refresh rate of that FFT will be slower. On the other side, a higher block length also means a higher frequency resolution. The delta F becomes finer, smaller. That is the balance that you have to find. Second, the window type. These are the two windows that are supported by the FX100, or you may also switch it off. And the x-axis scaling, linear or logarithmic, that may give you some valuable information about the behavior of your device under test. Last but not least, the averaging feature that would allow you to smoothen or to stabilize the displayed result in order to simplify or to make the readout easier. Well, I'm at the end of my presentation. I would like to point out that we have a couple of subsidiaries that you see here on that slide, together with independent partners all over the world. The independent partners are not listed in here, but if you have any question, if you need any support regarding FFT or regarding your test instruments, please let us know. We will be happy to support you. Our partners, our subsidiaries have lots of experience and skills, and we are very confident that we'll be able to solve your issue. I want to thank you very much for your attention. I hope I was able to answer most of your questions, and I would of course be happy to welcome you again in a future webinar. Goodbye, thank you very much, and see you soon, hopefully again.